see the same transformation. So this is our X and this is our Y. This is rotation about Z. Now the next thing I'm going to draw, okay. We are also going to draw the uh, the cross-sectional area. Okay, and the cross-sectional area, we are going to have three different types of cross-sectional area. Okay, so the first one, so when we view at cross-sectional area, I'm going to draw a transformation. It changes. So now this is Y, this is Z, and then because of the view that we're drawing, this is rotation in the X. Okay, so we're going to have three different cross-sectional area. The first cross-sectional area looks like this. Okay, like a T. And then we have our points alpha, beta, I, and point J. And then the next one, we are going to have an I. Oh, I'll make sure that okay. So again, this is our point alpha, beta, I, and then J. And then the last one, okay, is a box. And I want you to get used to all these shapes. Okay, it's a box. Okay, so again, the edges, alpha, beta, I, and also down here is J. Okay, and then the next one, I'm going to sketch the centroid, okay? The geometric centroid. Okay, so over here, this is the geometric centroid, right? Over here is exactly at the center, geometric centroid. Over here, this is the geometric centroid. And then vertical, this is the geometric centroid. This is our geometric centroid. And this is our geometric centroid. So this is our Z, 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 Y, 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 Y. Okay. You can use I'm going to ask your question and you can type your answer. Okay. By looking at condition number 1 and condition number 2, can anyone tell me which is symmetrical and which is unsymmetrical bending? If you feel that none is symmetrical, you can say A and B are unsymmetrical or A and B are symmetrical. Anyone? You can start typing. If you don't want to talk, I'm fine with that. Anyone? By looking at the loading conditions. No? Are you all there? Can you hear me? Can someone give me a thumbs up? Condition number 1, symmetrical. Okay. The answer is both condition number 1 and condition number 2 are symmetrical. Okay, both. Why? Is because the bending moment is applied on one axis only. If this thing were to bend, if the load condition 1 were to bend, I'm going to, this is just a sketch of how the structure will deform. The deformation pattern will look like this. This is just a sketch. Okay, this is just a sketch. So when you look at this is just the moment is only applied in the z-axis. Okay. The one on the left-hand side, of loading condition number 2, the deformation pattern looks like this. And for the deformation pattern look like this, we know that the moment about z, there's only bending moment in one axis only, in the z-axis. By looking at the moment vector, okay, we know that at the top is in compression, the tail end is in what? Tensile. Again, at this case, by looking at the moment vector, this is in compression, and this is in what? Tensile. I don't need to rely on formula. We already know by looking at the moment vector. That is the power of using the moment vector and not just relying on the matrix form. Moment acting in one direction is positive, the other one is negative. Then if you forget moment about z, moment z is minus in the front, you're done. No, you just focus on the what? Moment vector. So much easier. Okay, now based on the cross-sectional area now, okay, which one is symmetrical, which one is unsymmetrical? Is the T symmetrical? Is the I symmetrical or unsymmetrical? Or is the box, so I'll call this, okay, this is a T shape. Okay, this is the I shape. And this is the box shape. I won't call this the I shape. We usually call this a white flange. Okay. I want you to get used to all these names. Okay, white flange shape. Now, can anyone tell me which one is unsymmetrical? Or which one? Okay, let's go for unsymmetrical. Which one is unsymmetrical? Anyone? You are worried. Don't be worried, okay? If you're gonna make any mistake, we make it here. We learn now, okay? Can you all make any judgment? The T is unsymmetrical. Okay, now, Josh, I think you're the only one that's awake. The rest, I'm not so sure. Are you there? Okay. Josh, all of them, okay, all are symmetrical. Okay. I understand. I also when I was, in fact, when I finished my PhD, okay, which is much older than you, I thought the symmetrical and unsymmetrical is because of the loading condition and the shape of the structure. It is not. Okay. So whether symmetrical or unsymmetrical does not depend on the loading condition, like what we see on top. Okay, down here you have evenly distributed load, point load, you have gradient distributed load. No, it does not depend on the loading condition or the cross-sectional shape. Okay, it does not, because what I mentioned is all of them are symmetrical. Why is that? Because the formula used, right? The formula used is what? Stress X is equal to minus mz over izz multiplied by y. Okay, so the y distance over here, I will write down here, this is our y1. Over here, this is our y2. Likewise, this is our y1. And over here, this is our, up to here, I'll better draw it again. This is our y2. Likewise, this is our y1. And this is our y2. If we were to take any of them, okay, if we were to take any of them, and we are going to assume, okay, we're going to make assumption that moment about z is in this direction. Okay, all of them have moment about z in this direction. All of them. Okay, so what we realize that stress X at point alpha is equal to minus y minus, because it is on top of the what is on top of the neutral axis, is on top of the neutral axis over here, all relative to the neutral axis that I'm shading now. Okay, so this the one I'm shading, these are all our neutral axis. Okay, so stress X alpha is equal to minus mz, right? Minus mz over izz multiplied by y1. And this formula is also equal to stress X beta, right? Because the y distance from the centroid, whether is it alpha or beta, are the same distance. Okay, so this, when this is the case, this is where we call symmetrical, or for this formula, this is where we call centric, symmetrical bending. Okay, now if we now look at I and J, right, and we know that I and J, all of them are in the what tail end of the bending moment. They are all in what? In tensile. Okay, so when that's the case, stress X at point I, right, is equal to positive, because it's in tension, mz over izz multiplied by y2. And this happens to be also equal to stress X at point J. Both are in what? Both are in tension. So again, right, when this is the case, it satisfies the requirement of centric symmetrical bending. So therefore, symmetrical bending symmetrical bending is dependent on I'm rushing, I should not rush, is dependent on the what? Stress state. Are we clear? Not on the geometry, but purely on the stress state. Okay, and as I said earlier, when it's symmetrical, you only have what? One axis of what? Bending. Are we clear? Okay, we have to get this like pristine. Okay, we have to get this clear. So now if you look at this, you're like, okay, I can make the judgment what type of loading it is. Okay, it's going to be centric, by knowing that the bending is only applied on one axis, right? The bending is only about one axis, right? You know it is what? Symmetrical bending already. Okay, symmetrical bending analysis.